Last time I showed the floating bar tool changer assembly with the door panel. It's time to move on to the next objective, which I have suffered for a long time, the 3D printing fumes. In this episode, I'll discuss the Tophat system concept I left in the previous ending. The most important thing is the solutions to deal with the fumes. Hi, welcome to Slow Engineering, I'm David. The Tophat system consists of the Toolhead Wiring discussed in the previous video, an exhaust, a filter, and a C-pad connected to the printhead through a hose. Aside from the Toolhead Wiring, it also incorporates several fans. I will explain the scenarios these fans respond to and discuss their importance to the system. Before diving into the specifics of individual systems, I'd like to share my current setup for my Voron 2 and my experience with this machine. Some aspects need improvements or modifications for better performance. I installed an exhaust fan to create slightly negative pressures within the enclosure, aiming to keep fumes contained during printing and direct them outdoors. However, after over a year of use, I noticed that the exhaust fans remove too much air from the enclosure, causing the temperatures to drop significantly. This drop in temperatures can lead to warping of prints, mainly because the cooler airs affects the printed materials. I observed that warping mostly occurred near the fan, suggesting that the airflow from the exhaust fans contribute to the issue. The fan I use is the Noctua NF814 Industrial PPC 2000. Known for its high airflow, however, it lacks the pressures needed to maintain a slightly negative pressures in the enclosure, resulting in leaking fumes when printing with ABS. Additionally, the Voron 2 has inevitable gaps around for the axis where the belts passes through the deck panels and the gaps around the original panel door. These openings create challenges in maintaining proper pressures to keep the fumes contained. To minimize these issues, I built a new airtight tool changer door, which should help to create a more controllable environment with the enclosure. You might feel overwhelmed by the various conditions, so let's summarize what needs to be improved for the next update. First, we need to establish negative pressures to keep fumes contained within the enclosure, even with unavoidable gaps. This can be achieved by expelling the fumes outdoors or purifying the air inside the enclosures by suction. Second, we should create a mild airflow within the enclosures to minimize the disruptions caused by the fans. Third, it is essential to maintain a stable and easily controllable temperature within the enclosure to ensure optimal printing conditions. The systems must meet these criteria to provide better solutions for managing fumes and to improve print quality. Let's start with the issue of negative pressure. As I mentioned earlier, the exhaust fans I choose does not provide sufficient pressures to contain the fumes within the enclosure. As a result, the fumes still leak through gaps and openings. Therefore, increasing the pressure difference is crucial. While regular axial fans are less effective in creating this pressure difference, centrifugal fans perform better. However, centrifugal fans have some drawbacks, such as higher noise levels, lower airflows, and a tendency to create turbulence. So an axial fan or centrifugal fan. I have decided to focus on two other primary objectives, mild airflows and temperature control first to find a better option for the fan. Fans create airflows that affects the air inside the enclosure, whether axial or centrifugal. Axial fans usually have more airflows and contribute a fast airflow around the fan, which makes the prints near airflow warping. Centrifugal fans have more pressure difference, which might contribute to more turbulence when working. The same result makes the prints warping, however the temperature seems easier to control. By using a fan to create negative pressures, I can ensure that air is drawn back into the enclosure, resulting in minimal temperature loss during circulation. Additionally, these circulations allow me to integrate a filter system along the airflow paths to manage fumes effectively. The filter system will help remove particles and volatile organic compounds, improving air quality inside the enclosure. With these considerations in mind, the decisions become more apparent. I need a fan that can circulate air effectively to maintain the enclosure's temperature, while also allowing for the incorporations of a filter system. It needs to operate efficiently with these two features. Furthermore, the filter system requires adequate pressures to enable air passage. If the fan cannot generate enough pressures to push or pour air through the filter, the air will not be able to pass through it effectively. The internal compositions of the filter affects the amount of the pressures required for the fan. In the context of 3D printing operations, which generate small particles and various VOCs, an ideal solution would be use a HEPA filter with an activated carbon container. The HEPA filters effectively capture the particles while the activated carbons absorb the VOCs from the air. Both filters require pressures to facilitate airflow. As air passes through them, they create pressure drop. Specifically, activated carbon is more effective at capturing VOC if it has a greater surface area. This can be achieved by making the container longer or adjusting the airflow slower. A longer activated carbon containers makes pressure a critical factor when selecting an appropriate fan. While I can provide an actual estimate for the pressure needed for the HEPA filters and the activated carbon container, I assume the HEPA filter requires around 1 kPa with the robot vacuum cleaner filters, and the activated carbon container needs a similar amount. However, the actual pressures requires maybe less, as I have observed smaller HEPA filters and activated carbon setups functioning effectively with fans that only provide 0.06 kPa. Ultimately, determining how well the fan performs will require some experimentation. The filter systems now includes a HEPA filters and an activated carbon container. However, it is important to consider the filter's sequence and the fan's placement. Typically, the HEPA filters is positioned before the activated carbon filter. This arrangement allows the HEPA filter to capture larger particles first, enhancing the efficiency of the activated carbon and capturing VOCs instead of particulate matter. Regarding fan placement, if the fan is situated in the front of the HEPA filters and pushes air into it, most energy gets lost as the air collides with the filter, resulting in an uneven air distribution across the filter surface. In contrast, positioning the fan behind the filters to pull air through leads to a more uniform pressure distribution across the entire filter area. The filter system must maintain airflow to filter particles and fumes during printing. If the airflow is insufficient, fumes may easily escape outside the enclosure. I need to know the enclosure's volume to determine the necessary airflow for the fan. The inner dimensions of the 350 Voron tool are approximately 510 by 510 by 530 mm. Additionally, I need to account for a top hat for the Toolhead Wiring and 3 various inlets, which require around 200 mm to function properly. Once the top hat is included, the estimated total volume is 510 by 510 by 7 and 30 mm, resulting in a total volume of around 0.19 cubic meters. Regarding the fan selections, I needed to provide enough airflow to change the air at least 3 times per hour for effectively filtering. 3 to 6 air change rate is a good starting point, and if I print like high pollutions ABS or ASA, I can increase the air change rate to 8 to 12 ACH. Thus, with a volume of 0.19 cubic meters, I require a fan that can deliver at least 2.28 cubic meters per hour to meet this requirement. When selecting the right fan, it's essential to consider pressure and airflow. A comprehensive fan datasheet typically includes a pressure airflow diagram that illustrates how airflow performs at specific pressure levels. The fan must generate enough pressure to overcome resistance while providing adequate airflow to circulate air within the enclosure effectively. Initially, I mentioned my plan to position all the fans at the top of the enclosure. The reasoning behind this choice is relatively straightforward. Basics. The heated bed warms the air inside the enclosure without an active heater. Because hot air is less dense, it rises. Additionally, with the Voron 2 design, the top is the farthest point from the heated bed, which means that prints experience less air interference. I can reheat the rising air by placing the circulation inlet at the top and the outlet underneath the heated bed. This circulation method not only purifies the air within the enclosure, but also promotes more even heat distribution. Despite the filter system, is the exhaust fan still necessary? In my opinion, it also has its proper functionality. PLA prints can use the exhaust fan's high-volume airflow to keep the enclosure cool. This way, the door can be closed during the entire printing operation. Additionally, having an exhaust fan can expel air from the enclosure. One objective is to maintain stable airflow within the enclosure to ensure print quality. These stabilities can limit the air change rate of the filter system with the enclosure. A slow circulating system may take long to remove all VOCs from the chamber. However, with an exhaust system, the high-volume exhaust can efficiently remove all air from the enclosures and vent it outdoors after printing. Therefore, I still advocate for the installations of an exhaust fan. However, when the filter system is in operation, the exhaust pads must be sealed to restrict openings and maintain negative pressure. My proposed solution is to implement a damper to seal or open the exhaust pipe as needed. The final component is the CPAP fan, often called the power cooling fan. In my tool changer design, the power cooling ducts are attached to the printhead rather than the tool heads. This configuration allows for all the tool heads to utilize effectively CPAP cooling air without complicating the design. The fan is installed at the top to direct hot air towards the nozzle. All three fans serve different functions and are located on the top head. However, they do not solve the issue of achieving a stable flow, which I want to be a mild airflow around the print zone. While fans generate airflow when operating, a high-volume airflow could negatively impact print quality. To address this, I designed a shield panel in front of the fans to redirect the airflow. This shield is set back from the top panel of the top head, creating a buffer zone for the airflow before it reaches the fans. The shield is smaller than the top panel, which leaves gaps between the shield and the side panels. These gaps are positioned to prevent the fans from directly pulling air from the heated bed's top. Instead, the air is directed outward into the side gaps, enters the buffer zone, and then is redirected to the operating fans. By calculating the shield size and controlling the fan speeds, I can ensure a balanced and smooth airflow that remains mild as it transitions from the print zone to the buffer zone. Whether the airflow is directed towards the filter system, the exhaust, or the CPAP power cooling, the airflow passing through the gaps can be measured and controlled effectively. Small gaps can increase speed, leading to more significant turbulence that affects the prints. In contrast, larger gaps create less redirection of airflow. Therefore, choosing the right size for the shield is crucial. An airspeed of 1 to 2 meters per second is considered mild flow. For instance, I have an exhaust fan with a maximum airflow of 182.5 cubic meters per hour. It is paired with a shield measuring 470 by 470 mm and 4 gaps between the shield and side panels, resulting in a gap area of 0.0376 square meters and an airspeed of approximately 1.35 meters per second, which falls within the mild flow range. The fan's maximum airflow automatically determines the appropriate gauge size. What about the offset? The offset allows fans to draw air from the gaps between the panels. If the offset is small, the fans must work harder to overcome additional resistance. The air between the two panels behaves like fluid in a dock, which can be analyzed using the Darcy-Weisbach equation. However, I won't delve into explaining or calculating that here. Instead, I have a more practical way to determine the offset. While it may not be accurate, it's sufficient for this application. Similar to the previous series, smaller gaps require higher speeds to maintain the same airflow. This means that if I identify the smallest area along with the flow speed, I can calculate the necessary offset for the shield. I take the fan with the highest airflow and calculate its parameter. The parameter combined with the offset creates an area. I assume the airspeed is nearly the same as that in the gaps. This calculation leads me to an estimated offset value of approximately 85.38 mm for the shield. To account for some resistance between the two smooth, transparent polycarbonate panels, I'll round this to a more practical distance of 90 mm. By measuring the distance required for the Toolhead wiring and the shield's thickness, I can determine the inner height of the top hat. A height ranging from 150 to 200 mm will be sufficient. This calculation closely matches my previous estimation. This top hat system features filter circulation, controllable exhaust, and CPAP part cooling. Components like Toolhead wiring and LED strips are included to build a fully functional top hat. In my current setup, the LEDs are located inside the enclosure, which has caused them to burn out quickly due to the hot air. For this upgrade, I will place the LED strips outside the enclosure. The top panel and shield will be made from transparent polycarbonate boards so the light can pass through. Here are my solutions for my Voron 2 printer. Despite having small openings, I aim to keep the fumes within the enclosure. My approach includes a filtration system with circulation to maintain the enclosure's temperature. Additionally, I retain the exhaust fans for materials that requires a cooler environment and for quickly removing fumes. Lastly, I've ensured that the airspeed inside the enclosure is adjustable to a mild setting to prevent print warping during the printing process. High airspeed could lead to issues with the prints, so it's important to manage it carefully. It will be convenient to make all the fans and the systems be controllable to find the balance. I'd love to hear your thoughts on this concept. What features did I miss? Or which concept could be refined? Please leave your comments below. As always, moving forward.